Okay, well, it is my pleasure to introduce Dr. Thomas Greene, who's going to be presenting to us on the topic of the James Webb Space Telescope, which he's very well qualified to speak. And Dr. Greene, who's also an SMCAS member, as we found out, received his PhD in astronomy from the University of Arizona, is now an astrophysicist in the Space Science and Astrobiology Division at NASA Ames Research Center, where he conducts observational studies of exoplanets and young stars and develops astronomical technologies and instrumentation. Dr. Greene is also a co-investigator of the near-infrared camera in the mid-infrared science instruments of the James Webb Space Telescope and serves on the JWST Users Committee. While at NASA Ames, he has served as the director of the Ames Center for Exoplanet Studies, project scientist of the SOFIA mission, and chief of the astrophysics branch. Before joining NASA, he worked at the Lockheed Martin Advanced Technology Center on NASA astrophysics missions. Prior to that, Dr. Greene was on the faculty of the University of Hawaii, where he's a support astronomer and later director of the NASA Infrared Telescope Facility. He is currently co-chairs the U.S. National Academies of Sciences Committee on Astronomy and Astrophysics, and is a NASA representative on the WM Keck Observatory Science Steering Committee. So very well qualified to speak on the JWST for sure, and many other topics. And with that, we'll turn it over to Dr. Greene. The floor is yours.
Great, thank you, Marion, for that nice introduction. I'm going to share my screen. Believe it or not, I have a few slides and pictures to show. And let's see here, I'll go to portion of screen.
Perhaps I'm jumping the gun, but would you be kind enough to familiarize all of us again with who James Webb was?
I can do that. Believe it or not, I've got a slide on that. So while I'm doing that, I'll say that. So James Webb, oops, let me go back, was the second, this is interesting. Oh, there we go. All right. I think this is going to work. He was the second administrator for NASA. And let's see, can you see my slides now?
Yes.
Yes.
Okay, great. All right.
Yes.
He was the administrator from NASA from about 1963 to 68 or something like that. And so he oversaw the conclusion of the Mercury program, all of Gemini, and the planning for Apollo and the beginning of Apollo. It was really big times. One of the things he also did there was he really advocated and sort of fostered the growth of space science within NASA. With another administrator, that may not have happened. Because the MAN program, as we all know, is the big focus there. So we have a lot to thank him for fostering space science and making NASA the powerhouse that it is there. So yeah, I thought it was a rather fitting name. And this was named about 20 years ago, I think in 2002, when the first big contracts were let for James Webb. All right, so as I think Mike said that and Marion said, I'm also a recent member of the San Mateo County Astronomical Society. Happy to join you folks. I was at a star party a couple months ago. So
and we're glad to have you.
Thank you. So in addition to looking through telescopes from the ground, we now have quite a history since I think at least the late 60s of looking through telescopes in space. The big ones were in the 90s. NASA launched this series called Great Observatories over about 13 years that spanned 4 different observatories, different wavelengths. This is 3 of them there. So we have, let me get a laser pointer here. So these great observatories saw in visible light and ultraviolet Hubble, which we're all familiar with. It's been in operation now over 30 years. Chandra X-ray telescope launched in 1999, still going. Spitzer had a really good run. It was an infrared telescope. It eventually got too far away from Earth to send data back. There are worse things to happen. It was in this pretty unique Earth trailing orbit around the sun. So there are reasons to go outside the atmosphere. One of them is we can see a lot more of the electromagnetic spectrum than we can see through the atmosphere. In particular, infrared light is pretty interesting. And why do we want to study that? Well, just to give you a little bit of a visceral idea, here are some pictures in visible light of these meerkats and this crocodile. And then when we go to infrared light, we see the meerkats are glowing. They have internal warmth and they're radiating, and the infrared light picks that up. The crocodile is pretty faint because it's been in the cool water.
I need you to tap in.
All right, so this sort of shows that the visible light that we see with our eyes is just a very small chunk of the spectrum. It's only a little more than an octave in width. So, we can see blue light, which is a little over 400 nanometers, is as short as we can see. And we can see in the red out to 700 and some nanometers. H alpha is what, 650 some nanometers. And so that's only about a factor of 2 there. However, the whole spectrum is over a factor of 10 billion, from gamma rays out to radio waves. Radio waves are meters. Gamma rays are like 10 to the -4 meters. No, excuse me, 10 to the -4 microns. Quite a spectrum there. And Hubble saw, and it still sees, mostly in the visible, a little bit in the ultraviolet, considerably to the blue of what our atmosphere shows. I think it'll get down to 1,000 nanometers. No, excuse me, 100 nanometers, 1,000 angstroms. And it goes out to about a little short of 2 microns in the red. So it can see about 3 times longer than our eye sees in the red. And you can see significantly bluer, a few times bluer than what our eyes see. So this has really helped. Particularly stars have a lot of UV excitation. There's hydrogen has some big absorption features there. It's been very informative for learning about the universe. James Webb is going to see from about green in the visible out to pretty far in the infrared, 28 microns. So that is about 40 times longer than what the eye can see. And Spitzer saw even longer in the infrared. The infrared allows you to see through dust. Left here in this image of I always forget the Eagle Nebula, where it is M16 or M17. I've done some papers on M17, so I assume this is M16. And here we see these bright, young, massive stars in visible light, lighting up these clouds of dust from which they formed. In the infrared, in the near-infrared light, we can start to see through the dust. We see there's stars here. This is a star that you just can't see in the visible side. And you go to longer wavelengths, you see the dust itself glows because the dust has some warmth. Much different things. This little video shows an infrared dark cloud. So you see the dark part in the visible, and then this is the infrared part where you can actually see this embedded young star, and it has this jet of outflow coming out of it. This part here on the lower part of the screen is coming towards us, so we can see it in visible light. And we can see the far side in infrared light through the cloud. Infrared image of a galaxy is kind of flipped from a visible image. So in this image here, you see this dark lane in the visible, looks like is dust, is where actually all the stars are. The young stars are forming here. And you can see those in the infrared that you just can't see in the visible. So let's apply some of this to science. We sort of put together some big science themes for James Webb started back in 1990s, and we got a little formal about it by 1998. I was on this committee, this first science working group. And we knew that the most exciting discoveries would be things we couldn't dream of then, but we figured if it had good general capabilities to make progress in some big picture science topics, it would probably do okay. And those big picture topics are finding the first galaxies. So after the Big Bang, the first galaxies that formed after the Big Bang, the gas cooled enough, stars formed, stars came together to form galaxies. We want to see these early proto-galaxies. Then we want to study how these galaxies evolve from early times to the modern structures of today, which these very well-formed spirals and bars and whatnot. We want to understand how stars and planets form and how stars die. As you saw previously, that infrared imaging is going to be quite useful for that. And also to understand planets, planetary systems, and perhaps the origins of life. Exoplanets were discovered when we were doing this, but we had no idea we'd actually be able to get spectra of them. A few words about these different science themes. So the early universe, the Big Bang was really hot. The universe cooled after the Big Bang. And after about 400,000 years, it cooled to below about 3,000 degrees. And that was cool enough for hydrogen atoms to form. So the electrons combined with the protons, just about all of the early universe was hydrogen, and about 10% was helium, very little or zero heavy elements. And then eventually, the hydrogen atoms then could come together by gravity. As the universe cooled more, they had less thermal kinetic energy holding them apart. Gravity could pull them together. Stars formed, and then the stars started to light up the universe and reionize the universe. So this is the light from the stars is breaking apart the hydrogen atoms again. Eventually, the stars come together. They form these early galaxies, which we're hoping to see with James Webb. And then the early galaxies kind of clump together and form better structured things. This is what we can see with Hubble now. We can see back to about 600 million years after the Big Bang. And then eventually we have structures like we see today, like if we go out and look with our own telescopes. Very analogous. When I see this image, I think of Stephan's quintet or something like that. Also, as the universe expands, the light gets redshifted. The light expands too. And this is from the Doppler shift. The light that was emitted in visible wavelengths will come to us and be observed in infrared wavelengths if the objects that we're watching are moving away from us at high speed, which is true because everything in the universe is expanding. And now we know that expansion is actually accelerating. So another reason to look in the infrared is because visible light turns infrared. So this is just a little schematic here, sort of showing this picture of evolution from the Big Bang. Then there were the radiation era. This is when everything was very hot. Then the atoms formed, cooled off, and then stars and galaxies started to form. We started to get more structured objects. So when we look in any direction in blank space, we should see all that stuff. And that's what this next theme is this assembly and evolution of galaxies. So this is a simulation of a deep James Webb image. Hubble has seen similar things, but not quite as deep. This sort of shows we're going to have well-ordered things and also a lot of fainter things all in the same field. And we're going to try to piece those together as to which of these things were formed early in the universe and which are more recent and more nearby. Just again, that schematic picture again. So by observing enough of these and getting the redshifts, we hope to be able to identify these first objects, these first protogalaxies, the first groups of stars that actually came together, how these protogalaxies started to clump, and then they got bigger, spiral structures started to form, got better ordered, and then stars started to form to live and die in cycles, and then we get modern galaxies like we have around us in our local group. So, stars and planets. When Hubble launched, we were pretty sure that stars had disks around them. It was the only way we can understand star formation and planet formation from a theoretical perspective. And we had a little velocity information, but we didn't have any pictures. Hubble gave us the first pictures, those beautiful pictures of Proplids and Orion and other young stars with disks around them in the mid-90s. Now, James Webb is actually going to allow us to diagnose the composition of these disks, the chemical constituents, as well as seeing what planets are there. Also, the chemistry, and this will help us understand how the chemistry evolves from simple atoms into more complex organic molecules that eventually get onto planets. So the star formation and death scene, again, the infrared is going to be quite useful for that. This is similar to what you saw earlier, being able to see young stars. This is another picture of the same region. This is the Flame Nebula in Orion, right? NGC 2024. And this is a visible image from the Deep Sky Survey. And you see all the action is where you can't see anything. And this is where the young cluster is. And it's opaque in visible light, but in infrared, you see all these young stars. So in fact, I'm on a program where we're going to be doing sampling the population of these young stars in this cluster to try to see where the limit is for individual star and brown dwarf formation. Now, most of the planets that we know of now, I need to switch my pointer. Let me see if I can do that somehow. Oh, here we go. So most of the planets that we know of, we know about 4,500 confirmed ones, are detected by this transit method. If we get lucky and a planet goes in front of its host star so that we're aligned with it, and we see that, then the brightness of the star drops while the planet is transiting across the surface of the star. The Kepler mission discovered a few thousand planets this way, maybe I think over 3,000, 3,500, and we've had about 1,000 other ones through other missions and ground-based discoveries. So Kepler and K2 discovered many, and with Webb, we're going to use the same technique to actually characterize the atmospheres of those planets, because in addition to dropping in brightness, when the planet goes in front of the star, if there's a thin atmosphere that's around the planet, we can actually see through the atmosphere of the planet and how it modifies the starlight. I don't know if any of you tried to observe transits. I mean, they're pretty faint. A deep transit's about 1% of the brightness of the star. And the atmospheres, though, are about 100 times lower than that in terms of brightness relative to the star. So it's a tough observation, but we think we can do it. One of the things we're going to be looking for a bunch of different molecules in the atmospheres of these planets around other stars. One particular one that's around all of these terrestrial planets in our solar system, except for Mercury, is carbon dioxide. We know we've got a lot of carbon dioxide in Earth, right? So it's approaching 500 parts per million the last time I checked. I think 20 years ago it was 350 parts per million, or 300. So it's really going up. And it produces a very deep absorption. In fact, the atmosphere is pretty much opaque. And this is an infrared spectrum. So short wavelengths on the left and long ones on the right. This is about 15 microns. And you see that's carbon dioxide. Even Mars, which has a pretty tenuous atmosphere, its atmospheric pressure is about 100 times lower than what we have on Earth. It's like 7 millibars instead of a bar. And it's got this big absorption. Venus has a huge one because the pressure is really high. And some of the CO2 probably came when it boiled off its oceans in its runaway greenhouse. Now, you may notice Earth has this other feature that these other ones don't. This is an ozone feature at around 10 microns, 9 point some microns. And its ozone is O3, which is basically an oxygen molecule with another oxygen atom on it. So it's a proxy for oxygen. So this tells us that there's some non-equilibrium process, because usually the oxygen wouldn't be combining with itself in an atmosphere. It'd be forming into stuff like carbon dioxide, it'd be forming with carbon. So this shows an atmosphere out of equilibrium. And we know that life is causing that here on Earth. So it'd be pretty cool if we can see that on other planets. We are going to look for it. And one system is this TRAPPIST-1 system. This is about 12 parsecs or 40-ish light years away from Earth, where it has 7 planets. Those are the same planets here. This is the distance from the star in terms of the flux. Earth is here, 1 astronomical unit away, and 1 solar flux is Earth. D is pretty close. It has the same flux as Earth. The density is a little lower. The planet's a little less massive. And B is a little more like, B and C are more like Venus, and F is more like Mars. We're going to look at all of these in the first year to try to do various observations to look for atmospheres around these. Now you're curious about the observatory hardware. This is a picture. I'll go into more details later, but it doesn't look like other telescopes that we're used to. It's got a mirror, right? Primary mirror, secondary, sends the light through this hole here, the central hole in the primary. The instruments are on the back. It's a 3-mirror and a stigmat because it uses a wide field. Then there's this huge sunshade. This is like the baffle. It's like the tube on our telescopes, right? And the spacecraft is on this other side. This is the side that's always facing the sun and the Earth. And I'll show you in the orbit how that works later. And this side is always in the shade, and that allows it to cool. And it gets pretty cold. This is some pictures of the telescope. I think this was at Goddard Space Flight Center, and they're first assembling the telescope around 2016, 2017. This is with its wings folded up. This is Northrop Grumman when it was mated to the spacecraft with the sunshade there. These are more recent. It just left Northrop last summer. So James Webb is a lot bigger than Hubble. 6.5 meters diameter versus 2.4 meters for Hubble. It's got about 5 times the light collecting area, and it's about 3 times the spatial resolution because at the same wavelength because of the larger aperture from the diffraction limit. Don't have to worry about seeing. It shows the 2 sides. As it showed before, just how the sunshade works. There's 5 layers in the sunshade to allow it to cool off on sufficiently on the side close to the telescope. Also, in case any micrometeorites go through, it won't create any sort of path for radiation to get through. And then solar array, leave that for power, antenna, and the spacecraft here. That's always in the sun. The mirrors are just like the mirrors on our telescopes, right? We have mirrors made out of beryllium and coated with gold. So maybe not exactly amateur telescope mirrors. There's it's a big telescope going into space. It has to be really light. Beryllium is the atomic number is 4. It's very low on the periodic table. So that's it has to be beryllium because it's light. Also very thermally benign. Gold is because in the infrared, gold has really high reflectivity. So it's better. The reflectivity is better than 99%. Aluminum here, you see in the infrared, at best is about 98%. But the big deal is the emissivity. So it's 1 minus or 100% minus the reflectivity. So the emissivity of gold is only about 1%, and aluminum is like 2%. So that's like twice as much radiation coming from the telescope itself with aluminum than if it's gold. That's a big deal because the telescope has some warmth. It's cool, but it's not 0 degrees. And we don't want to have any kind of radiation from the telescope swamp that of the objects that we're trying to observe. The alignment is going to be pretty tricky. We've got about a month plan for the alignment. Actually, there's a little more time budgeted. We're hoping we can do it in a month. So when we first turn it on, we will going to look for the stars from each of the segments. There's 18 segments. We think we'll see about half of them when we first turn it on. We'll have to search for the other ones, and then we can move all the segments individually for doing these searches. And then we'll find all of the images from the segments. We'll do like a coarse focus sweep, and then we will start stacking them into a single point spread function. Then we'll get all of them piled together, and then we have to do a fine phasing of the mirror, which we're using these dispersive elements for in these funny little spectra that we'll get to be able to actually phase the edges of the mirror to make all the segments work like a single optic. This is a little comparison of how James Webb compares to a large ground-based telescope like Keck. So James Webb has got a 6.5 meter. Keck is the biggest ground-based telescope at 10 meters. It's got about 3 times the area as James Webb, but James Webb is still pretty big. James Webb is faster. It's f1.25 versus f1.75 for Keck. Now, this, one thing to keep in mind here is that each segment isn't anywhere near this fast. So because there's like 6 segments across the mirror, each segment is a lot slower in its own F number, but they combine to make a very fast telescope. This is the wavelengths over which they operate. So in the green out to the mid-infrared, and from the near UV out to 5 microns. 18 segments for Webb, 36 for Keck. The Keck segments are a little bigger. Now here's an interesting number. So even though the Keck ones are lightweighted, each segment weighs 20 times that of what a James Webb one weighs. And this is the beryllium working for you here versus the 0 door of Keck. The whole telescope for James Webb, including fuel, is 6 tons, 6.2 metric tons. And Keck, just the rotating part on the azimuth bearing, is 270 tons. And a little more expensive to operate, but not as much as you might think, because we do get about 9,000 hours of observing per year. This is sort of assuming assuming 10 years of operations for James Webb. We have science instruments. The light has to get collected somewhere. So this is wavelength down here. Again, they all turn on around 600 nanometers. And the reason why we can't go lower is because the detectors don't work. We're using these for 3 of the 4 instruments. We're using these near-infrared detectors that go from 0.6 to 5 microns. They're these mercury, cadmium, tellurium mixtures. And then for the mid-infrared instrument, that uses the longer wavelength. This is a photoconductive detector that goes from 5 to 28 microns. So there's a near-infrared camera and a near-infrared imaging slitless spectrograph, and the mid-infrared instrument are all doing imaging, and they all do spectroscopy, even the camera. This shows the fields of view. This is superposed on M51, which you're probably all familiar with. NIRCam has 2 nearly identical fields. It's very redundant because we have to use that to align the telescope. This is the spectrograph's fields for its multi-object array, the imager on the mid-infrared instrument, and the near-infrared imager and slitless spectrograph. This is the actual how they map on the sky around the whole of the telescope. That other one wasn't accurate on the sky. There are also coronagraphs you can see here. This shows how the slitless spectra get spread out, and this shows how these spectra in the microshutter array of that spectrograph get spread out. We built the near-infrared camera at Lockheed Martin in Palo Alto. It is very redundant, so it almost looks like this is a mirror, right? Because we've got a mirror image of optical bench here, and all the optics attached to it there going down, and the same thing up here. And the 2 benches were assembled with the optics and then put together back to back. If you look carefully from the right angle, one of these benches says "Go Girl Scouts." This is part of our education and public outreach. This is the detector array being fabricated at the University of Arizona. This is a mosaic of 4 detectors being put together. And this was led by Professor Marcia Ricci at the University of Arizona. The near-infrared spectrograph is a contribution from the European Space Agency. It's carbon silicon carbide instead of beryllium, like NIRCam. You can see the gratings there. This is the grating wheel assembly. And it's got this pretty tricky gizmo in it. This is actually developed at NASA Goddard. It's called a microshutter array. So this has a whole bunch of little apertures that can be opened. So they're pretty small. They're like 100 microns. So you can, stack up 10 of these in a millimeter in the long direction. And the telescope image is going to be, it will image the field onto here, and then you can open these up where you have an object whose spectra you want. And you get something like this. So here's like the image, and then you open up these microshutters in different ways, and you get these spectra of objects that you want to observe. And you just can't have everything open because then all the spectra overlap. But if you judiciously choose what objects you want to observe, you can get multiple spectra. The near-infrared imaging spectrograph was developed in Canada. It's pretty similar to the near-infrared camera in some ways. It has this really neat cross-dispersed grism element that will be very handy for exoplanets, and it has some other spectroscopy as well. Mid-infrared instrument here is a joint US and European project. It has to be colder than the rest of the telescope, and that's why it's wrapped in this foil here, because it's trying to insulate itself from the rest of the telescope. It's cooled by a cryocooler, and it's a closed cycle cryocooler. Picture of the telescope when it was assembled at Goddard Space Flight Center in the clean room. Secondary up there. Let me get realize I'm not using an optimal pointer. This are all the instruments were integrated in this instrument module. That's the spectrograph there. This is the camera, near-infrared camera. That's the nearest instrument. That is the mid-infrared instrument. That all got sealed up here. There's a radiator and whatnot attached here, and then that gets put onto the back of the telescope. This is the whole observatory. So the telescope with the secondary folded up, the wings folded back, and the sunshade extended. This is with the sunshade retracted, and these pallets are getting folded up. The yellow stuff is ground support equipment. That's not going to fly, but it's useful for moving things around. And the telescope was designed to operate in zero gravity, so we have to be pretty careful when we're actually moving it around in Earth's gravity. So hope that helps explain why why this telescope looks so funny. And getting close to wrapping up here. So thousands of people developed Webb. I saw one number recently. It had about 1,200 people involved in the effort. There are also people in Hawaii, which is, I think this thing is showing, they're on our near-infrared camera team. And so us all over, including Europe. And right now, it's over here in French Guiana at the European Space Agency spaceport in Kourou. And it's, I think today it got integrated onto the Ariane 5 rocket. The fairing goes on next, and then it gets rolled out. So I try to give you a picture of what we thought Webb might do back in the old days. And this shows what people have actually asked Webb to do in the first round of proposals. Pretty interesting division, about 25% exoplanets. These two is about 25% stars. These are different kinds of stars, the physics of stars themselves, and then groups of stars, studying groups of stars. 26% galaxies, and the rest is cosmology, supermassive black holes in the solar system. So about interesting sort of even division between a lot of science categories. Where's it going to go? It's going to go out here at Sun-Earth L2. This isn't drawn to scale. So the sun's here. Earth's one astronomical unit out here. About 1% of the distance toward the sun, you have this L1 point. You can think about that as where the gravity of Earth and sun sort of balance. There are a few observatories here. There's some solar observatories, and there's some Earth observatories here. I think Discover Earth Observatory is there. Out at L2 is similar distance. So it's only about 1% of the distance, about 1 million miles away from Earth and away from the sun in the anti-sun direction. There's this quasi-stable point, Lagrangian system. James Webb's going to orbit around there. There's some other astrophysics observatories orbiting around there too. Planck, Herschel, some other things, I forgot. This shows how it fits into the fairing of the rocket. This is why the mirror sides have to fold in, because it's a 5-meter fairing and we've got a 6.5-meter telescope. Ariane 5 is quite a capable rocket. It's about 50% more launch capacity than a Falcon 9, for example. So if we're on schedule, it's going to launch at 5:20 Mountain Standard Time. So that's 4:20 a.m. Pacific Time on Wednesday, December 22nd. So that's 12 days from now. This is, so it's going to take 6 months to really get the thing together. It's about a month for deployments and cooling. And then we commissioned the telescope for a, hopefully we'll get most of this done in a month. We'll be able to start some of the science instrument commissioning early. That's our plan. And then we commission the instruments. This shows the sequence. So after about half an hour, it separates from the rocket, and then the solar array comes out. After a couple days is when the sunshade pallets come down, I think about 2 days. Then after about a week, the sunshade gets tensioned, and then it gets popped up this way. After about 10 days, the secondary comes down, and then the wings fold out. So within 2 weeks, we've got all the major deployments done, hopefully. And this shows sort of the same sequence here, going from Earth where all the different deployments happen. And it takes about a month for it to actually get into its final orbit around L2. And by then, it'll be cool enough to actually turn on the instruments. At about launch plus 36 days is when we turn on the camera and start, we'll do a brief checkout of the camera and then start trying to hunt down stars from the mirror. So wanted to close with asking just making comment about how the public can benefit from Webb. And I think it's going to address questions that people have had since the beginning of time. You know, the Greeks documented this. We've been asking ourselves, what's in the universe besides us? How old is it? How did we get here? Are we alone? Hope I tried to illustrate some of that from the scientific perspective about galaxies, stars, planets. We'll be able to see whether some of these planets are like and unlike Earth. Also, just kind of more viscerally, one thing is that, you know, as we know, most of the atoms in our bodies were created in stars. And so we should be pretty concerned about what's going on in the universe, given that's what we're made out of. And then on a more practical side, it's also advanced our scientific technology people here in the Bay Area, California, and all over the world help build the Webb, we really helped kind of advance astronomical technologies that are going to benefit ground-based and other future space observatories. And we brought a lot of people together. Like I said, over 1,200 people from many countries have worked on Webb. And hopefully at Science will bring many more people together. So that's what I have, and I'm happy to take any questions.
Is there access to your slides or to these links that to which one can go?
Yeah, I can provide the slides if you like.
I think that would be useful. To be perfectly honest, I mean, I've been engaged with astronomy and with telescopes for many, many years, but it looks like this one is a gigantic leap actually above the technology of other instruments that with which I've been familiar. And I can understand that that was bound to happen eventually, but it would be useful to be able to look at them, you know, at somewhat greater duration and examine the parts and components and so on. Too bad we don't have your narration to go with it. Well, actually, I guess we do.
You do, yeah. You recorded this.
Yeah. Okay. Yeah, if you could arrange to provide a link where the slides could be viewed, perhaps send it to Marion and he could put it up on our groups.io or possibly our YouTube channel, something like that.
Okay.
The website, actually.
I can send a link. Go on.
I had a question on how the data might be processed. I was just curious, because if we're taking all the infrared data, I'm wondering if in some cases for looking at the very distant galaxies, are we then trying to then take that infrared data and calculate like how much it stretched from the expansion universe and then change that back to try and see what it looked like in visible light?
Yeah, sort of. So we do want to measure redshifts because the redshift, so what we'll do is that there's some really honking strong spectral features from hydrogen in the universe. And by looking at their spacing, because we know from the laboratories, you know, what their intrinsic wavelengths are, but we're going to see them in much redder wavelengths. So things that we see in the ultraviolet, like Lyman alpha at 1216 angstroms, you know, could be 10 times longer in a James Webb image, which means it's got a redshift of 9. And then by looking at what the real wavelengths, what the measured wavelengths are versus the lab wavelengths, we'll measure the redshifts. And then that tells us how far back, you know, in time, because of the expansion of the universe, that this light was emitted. So we'll be able to sort of piece together the sort of the line of sight from that.
Yeah, I get the bit on sort of measuring the redshift, but I was just wondering if, because a lot of times with infrared, right, we translate these infrared waves into, you know, a visual spectrum that we can see, right? But sometimes those colors are just sort of picked.
Oh, I see what you're saying. Yeah.
So I'm wondering if we're trying to actually get what the real light type images by using the redshift to figure out how much to compress the wave back to see what it would be in the light that got emitted.
Well, yeah. Well, from measuring the redshift, we know what the intrinsic wavelengths are. You know, so I mean, we know the H alpha is 65, 63. Is that the number? Angstroms, and Lyman alpha, etc. So you could then, if you wanted to, yeah, if you have an image of an object and you know its redshift, then you could color the lines based on that. But you'll miss out some interesting things, though. I mean, you'll miss out ultraviolet, which we can't see.
Yeah, that's true. Yeah, I was just curious if that was one of the approaches that they may be using with this or not.
Maybe for outreach, you know, just to communicate that. I bet people will do that with H alpha lines because, you know, they're pretty red color. But again, you know, I guess it'd be informative, but if you really did a true color mapping, then we'd only see a really small bit of the actual recorded spectra.
Yeah, right. Cool, thanks.
Sure.
On that same vein, will the data that's being collected be made available somehow to the public for their own science and processing, like some of the other missions do, or will it be held and studied and then parsed out later to the public after the scientists have had their crack at it?
The answer is yes. There's a archive. Now, some of the data will be proprietary for a year. I guess they don't like that word, exclusive access period. So, but some of these large programs will be made public immediately. And you will get our data. I'll put this in the chat too. I did put the Webb blog in the chat, but here's this Mikulski archive, MAST. So as soon as the data become available, they'll be available here. They're searchable. You can actually, search by instrument. You could search by position. I don't know if it'll search by like common name. Yeah, I think it will search by resolvable name. So if you put in a name Sinbad can resolve, it'll show you the observations there. And it also shows you, I think, little postage stamp pictures of what the data look like. And you can download then the full data set too. Their data are available in different levels of processing. You can get it all the way, I think, from the raw products, which you probably don't want because they're really large and you have to put them together to sort of see the integration during the exposure. It's probably better to get them after after level 1 or level 2 or level 3 in the pipeline, which put together higher and higher products, including full mosaics in the level 3.
Any other questions?
Yes. So as I understand it, you said that the wavelengths of James Webb were essentially the same as Spitzer, but that Spitzer had about 1/10 the diameter of James Webb. Are those correct, or have I missed something there?
Yeah, you're getting close. So yeah, Spitzer was about 85 centimeters, and James Webb is 6.5 meters. So James Webb has about 50 times the collecting area that Spitzer did. And James Webb can see a little shorter than Spitzer did, but doesn't see nearly as long. So Spitzer also had 2 phases of operation. Its much longer phase only went out to about 5 microns. So James Webb will see longer than that.
So I mean, given that there's arguably primarily only a size difference, what are the qualitative differences that allow Spitzer to do stuff that's that allow James Webb to do stuff that Spitzer could not do? Is it another 15 years of technology and questions asked, or are there greater subtleties in?
Great question. So a factor of 50 difference in size is nothing to sneeze at, though. Okay. And also it's more than 50. Sensitivity goes as diameter to the 4th power. Okay, and we're talking about a factor of 8 diameter, so that's 64 squared in terms of sensitive in sense of time to do the same observation. So we can do much deeper observations. Spitzer actually did surprise some people. It saw some stuff in the early universe, and that got a lot of people excited for such a small telescope. We have more sophisticated instruments with Webb. We have more advanced detector technologies, particularly less than 5 microns. Bigger areas, we have better spectroscopy. There are observations with Spitzer for these exoplanets where we could only take pictures of these planets in filters. And we're trying to guess from these filters whether there's methane there, whether there's carbon monoxide there, carbon dioxide. It's pretty hard. With Webb, we'll actually be able to divide that light up and get spectra with the same quality that we had images from Spitzer. So it's really going to help us explain a lot of what we discovered with Spitzer and be able to, figure out better what's really in a lot of these.
Given the fact that Webb is going to be remotely located with regard to Earth, there's not really any opportunity to service it or repair it if something goes wrong. Where would you say the most significant points of failure would be in the design?
There are over 300 points of failure in the deployments. So we will know a lot after the first month. So all that has to happen in the first 2 weeks. A lot of smart people have thought hard about the stuff they thought was hard. I'm guessing that some of the stuff they thought was easy may not work exactly right because they didn't put quite enough horsepower to thinking about it. We'll see. That's usually the way these things work. We hope that the mission is ultimately limited by fuel. We saved some mass, and we had enough mass left over to completely fill the fuel tanks. They're full now in Kourou, and we hope there's up to 14 years of operations from the fuel. So yeah, there's a question in the chat that's related, saying Hubble had gyroscope issues that required maintenance a few times. Has this advanced? So we think the reaction wheels, I don't think we have gyros per se. It's also, we don't have like magnetic torquers because we're not in the Earth's magnetic field, but these reaction wheels shouldn't be the life-limiting factor with James Webb.
Yeah, they were with Hubble, weren't they?
Well, the gyros are, and they had to be replaced. I think the last mission was in 2009, right? The last servicing mission.
Yes.
So they've had some spares and they're still working. So I think they're even working in, I think it's at least a 2 gyro mode. I think they're using 2 and keeping 1 as a spare, and that's pointing pretty well. So that is already almost 13 years. So, you know, we can conceive that they should work well for the 14 years of fuel that Webb has.
It looks like we have a question from Oliver. Oliver, you want to ask your question now?
Yeah, hello, thank you. So I'm trying to better understand how the micro shutters work. Is each micro shutter cell mapped to 1 or more specific pixels? And how does closing some of them keep the spectroscopic data from obscuring the data from the other desired objects?
Well, each shutter is mapped to a spatial point on the sky, not a pixel on the detector. The way they work is that they're before any kind of dispersive element. So when light comes down through a point, it gets spread out, okay? And then the problem is if the shutters aren't there, if there's light to the next point, it's going to get spread out too. So 2 points close in an image will have overlapping spectra if there's a lot of dispersion there. And the micro shutters allow you to do is say, I want source 1, not source 2. And you can close the shutter in source 2, you open it in source 1, and then it allows just that 1 point to get through the optics and spread the light out and form on the detector. Now that said, we do have some modes that are completely slitless, but you don't want to use those on crowded fields. So we're like, for example, there's some really deep fields. We want to be able to see some early universe objects, and we don't think there are any stars there. And we want to just see if there are any emission line objects from the beginning of the universe, and then we'll use slitless there. But for a crowded field, you want to use the microshutters.
So if you have a set of objects you want to study all at the same time, does the design of the shutters dictate how close these objects can be in the sky in terms of without interfering with each other?
Yes, and also when you make your observations, you can specify the rotation angle. So, you know, James Webb is an alt-az telescope, and it's going to have different field rotations at different times. So you could pick an optimum position angle so that because the dispersion is always going to be in one direction relative to the detectors, and that's going to change on the sky. So if you have a bunch of objects in one configuration, a non-random configuration, then picking the optimum angle could help that.
Okay, thank you.
Question about being on L2, which I guess is fairly far from Earth. So I gather the JWST will just be continually viewing. It's never obscured by any moon shadow or Earth shadow or anything else. Or are there some outages that some other planetary transit or something that's going to obscure it at some point? And
no, that's right. There aren't any occultations of what the telescope can see. We at any given time, though, it has you can see about 50% of the sky. We can't tip the telescope close to the sun, obviously, and you can't tip it too far away from the sun, but it can spin around on its axis, so it can look around. I wish I had a model here, but maybe I should do that for my next talk, is get an actual model to show. But so it can look at the poles, the ecliptic poles, pretty much anytime. But for a given direction along the ecliptic, it can only see for about 2 months of the year.
Ah. Okay, and also out, you mentioned that there may be some other objects out in L2. Is that getting crowded out there? Or is that like a communications issue? You got interference? What's any issues there?
Good question. Yeah, I gave this talk for Lowell Observatory. I got asked that question too. That's a great question. So the observatory doesn't actually sit at L2. L2 is only a quasi-stable point. It orbits around L2. The radius of the orbit is 50,000 kilometers. And there are fewer than, I think, 10 observatories at L2. Herschel, Planck, WMAP, some other things that I'm forgetting about right now. So, 2 pi r with r being 50,000. So that's like 300,000 kilometers circumference divided by 10 objects is like 30,000 kilometers between the different observatories. So I don't think we're going to run into traffic jams.
Yeah, is there any, well, I'll call it L2 police or international committee or organization that kind of governs the use of that, or is it just so uncrowded that's not a concern at this point?
Well, there's no commercial interest, so I don't think we have any governing. I mean, look at low Earth orbit. They're pretty much kind of a cowboy Wild West situation there, particularly with all the new the new constellations of these small sats like Starlinks and whatnot.
Yeah.
People blowing stuff up left and right.
Okay, so it's just, what I understand, probably informal coordination between the science agencies that have stuff out there to make sure you're not stepping on anybody's toes or stomping on radio frequencies or such.
Right. So I think the only people that have launched there so far have been NASA and the European Space Agency. I don't think JAXA, the Japanese one, has, or Russia or China. Russia may have something. They may have an astrophysics observatory there. But yeah, I think that and it's only really astrophysics, I think, is of interest, because Earth science, solar science, probably a lot more interested in L1.
Is there any sort of natural, asteroid fragments or debris that gets captured into L2 or in orbit of it? Is that like a space dust magnet or something?
I don't know. I would think that its potential well is pretty shallow. I think the bigger issue is probably just crossing orbits with other things that have like strayed from comets and whatnot around the sun. I think that's really going to be the issue there for micrometeorites. Dust.
Looks like we got another question in chat.
Oh. Mm-hmm. Okay, I'll say that if you were looking at habitable exoplanets, the only way you'd be able to detect if life is there is some kind of alien megastructure. Is that correct? Otherwise, it's marked as possibly habitable and are possibly inhabited. Yes, on the characteristics of the atmosphere. We don't know of any alien megastructures. I don't know. We could tell. Hopefully, we'll be able to tell whether there's non-equilibrium chemistry going on in planets, and we can then say whether we could explore different pathways, do some sort of analysis to figure out how likely it is that life could be driving that particular non-equilibrium scenario that we're observing. But life could also be pretty different from what we, are familiar with here. Every time we've assumed that the universe is like Earth, we've been wrong, or most of the time.
Right, and we'll be able to do that because we're going to be able to look at the atmosphere with this guy, right? So we'll actually be able to see some of the chemistry in the atmosphere.
Yeah, in particularly the bigger planets, we could do that well. We can do that for things the size of Neptune pretty well. Things smaller than Neptune get harder. Things the size of Earth get pretty hard. TRAPPIST system's a little different, but the TRAPPIST planets may also have been roasted by their M star. We'll see. I've got a program actually that's going to look for the CO2 in the atmosphere around TRAPPIST-1b, and we'll actually be able to see hopefully thermal emission from the planet, and we'll be able to see whether it's at a temperature consistent with bare rock or reasonable geologic materials, or whether there's a cooler atmosphere absorbing there.
Yeah, that's cool. I've been reading about this because I've heard this was going to be one of the big studies initially when this thing comes out. So very, very, very cool to see what happens out of that data.
Yeah.
If I recall, TRAPPIST is a red dwarf. I think they're saying they're thinking that the planets are probably tidally locked. Is that right?
Yeah, the planets are supposed to be all tidally locked, but the amount of energy that comes off there, they still think it's all going to work. And when the study I was checking out was talking about, even though planets are tidally locked, if they have an atmosphere, the hot side will, some of that energy will flow to the cold side, just as the nature of hot and cold. And so
Yeah.
the only the very tips would be extremes.
Yeah, we've actually measured circulation in some exoplanets, and you can see like the hot spot on the face of the planet is displaced from the substellar point, and that's due to a wind circulating material around. Also, it looks like clouds will form on sort of like the terminators, the evening and the morning terminators.
Yeah, that's basically what the thing I was reading about was trying to tell me. I just can't explain it like you can. Looks like there's one other question here from John Gilbert. Says, what happens to it in 15 years or so when it runs out of fuel? Does it stay forever around L2 or fly away?
Good question. I imagine it's going to kind of be around L2, but the orbit is going to increase in size because it's not going to be able to do the station keeping. So late one night when I'm in the mission control room and we're going through a boring period of like, say, lost contact with a deep space network or moving between stations, I'll ask one of the mission operations people that. And if I remember, I'll get back to you.
Okay.
Could you suggest what might be the 2 or 3 most amazing discoveries or revolutionary, shall we say, outcomes that might come out of the 15-year project here?
Things we can't imagine. I think that's the most likely scenario, things we can't imagine now. I think it'll be really cool if we determine whether some of these planets like Earth have atmospheres, and whether, what the chemistry is like in those atmospheres, whether it's more boring equilibrium stuff or whether there's something there keeping the chemistry out of equilibrium, which could be life. Getting some idea of what these earliest objects were in the universe. It's like, are these how massive, how luminous were these stars? We don't really understand how stars can form just with hydrogen and helium, because it's hard to understand how they could cool without having metals, bumping into metals that could then radiate. I don't know. What are the lowest masses stars to form? What's the process that determines the number of stars to form in a cluster? It's like, why is there a peak around a few tenths of a solar mass? And what's the nature of it's just like, I don't know, but hopefully we'll have a better idea. Just to give you an idea of the scope of the science. So just in the planet field, this is one of the areas I work in the first year, Webb's going to observe about 70 of these extrasolar planets. And that is about the number that Hubble has done in its whole career. And we'll have much higher quality data. Each wavelength will have better signal to noise, and we'll have much broader wavelength coverage. So it really is a new ballgame.
Okay. Anything further, folks?
Yeah.
I'm sorry, Oliver.
Go on, Oliver.
Thank you. Aside from the exoplanet studies, will the resolution of the telescope be able to detect spatial surface variations and cross the star disk images, or is that they're too far away for that?
Yeah, it's too far away from that. People are starting to do that on the ground with interferometry. Didn't the club have an interferometrist from Chera talk? That's where you need really big baselines, bigger than the 6.5 meters of the mirror. Now, one of the way we could start to probe that kind of stuff is by using things like transiting planets, because if you have a planet, particularly if you know there's no atmosphere, and it moves across the surface and you see variations in the flux, you know then that it's like running over star spots and whatnot. But
Okay.
That's about as direct as we can get.
Okay. Does anyone else have a question or something to add?
I was just going to say thanks again for the lecture. This is like the second month in a row we had super great lectures. So very exciting. Thanks for coming.
Yeah, it's fascinating and very, very timely, of course. So
Well, you're welcome.
we really appreciate
And
it.
I'm sure we'll all be virtually together at 4:20 a.m. on December 22nd, right?
Yes.
We hope so. Okay. And look forward to seeing a lot of you in person at a future star party.
Yeah.